Hi, my name is Callum Hunter and this is my Engineering Design Project 1 presentation. So this is my contents page, so we'll have a bit on the background, some construction and operation, code development, practical demonstration, additional features and my ideas for the future. So for starters, the background, the Asuro is a small little robot. You start off with like a circuit board and you build it up, and then you can program it and get it to do all sorts of things that you want it to do. Then we have the Atmega 8, which is the microcontroller that the Asuro uses. The Atmega 8 uses Harvard architecture, which means it has memory for the data and the instructions. This is better than von Neumann architecture because it stops bottlenecks. The motor we use in the Asuro is a DC motor, which works off electromagnetic induction. Basically Fleming's left-hand motor rule, so it has a magnetic field. When you apply a current across it, a force comes out. The specific one is a H-bridge motor, so basically it works with 4 switches, so when certain switches are used together, it'll cause a different, so when certain switches are used together, the current applied goes through the motor a different way, which allows us to make the robot go forward, backwards and stop depending on the switches we use. Next we've got the odometry system, which works from an LEDs and phototransistors. So basically we have a circle with black and white segments. The LED will send out light and the phototransistors will collect it after it's bounced off the circle, which allows the microcontroller to work out the distance it's travelled based on the data it receives. And then we have the line following. So the line following is similar to the odometry. It is an LED that sends light out and 2 phototransistors that read the values that come back after the light has bounced off the floor. So when the when the light bounces off the black surface, it'll give a different value to when it bounces off the white, which will tell the motors to speed up to get it back on track, back on the black line. So next we have the construction and operation. So the order of construction. So I started with the axles, and then I used the way I went is I used the smallest parts, because then when I put them in the circuit board, they didn't drop out while I was soldering them, so I didn't have to hold them. A problem I encountered with the axles is I found it hard to get them to stick on the board. The way we got around this was I used flux and had the soldering iron at a higher temperature, which managed to get the solder to stick around it and stick it to the circuit board. Then we've got the weekly challenges. So the weekly challenges, you start off with driving the robot a meter, and then from there you build up to make the robot driving a square, then a figure of 8, and then using the sensors and then using the line following system. So the problem I had with the line following system was sometimes it didn't stay on the line very well, and that was because the phototransistors were different distances away from the LED, so they both got different values even when they was both on the same surface. The way I fixed this was I just moved them so they were the same distance away, which seemed to fix the problem. Code development. The way I develop my code is I use flowcharts, because I think they're really easy to follow because they're visual, and it's just everything's broken down into steps and it's easy to follow for me. And then the way I make my programs is I start with a basic program like in week 1, and then for week 2 I build on that, and then I test and record the data. So for example, when the robot was driving further than a meter, I'd reduce the values used in my code, and it'd drive less than a meter, let's say, and then I just edit and retest until I got the program working how I wanted it, until it was driving an exact meter. So this is a video of my robot working. There we go. So as you can see, the robot drives very smoothly, and it works well. It does get back on the line when it goes off. We'll see that in a second. So the way it does this basically is by driving in a circle over and over until it refines the line. So I just move it here, so you'll see it work now. So it comes off, and then it refines it by just driving in a circle. The way I could make it more smoother is if I was to increase the amount of intervals that the phototransistors read, because then I'd have more data and it'd be more accurate to the line. However, this could make it, so that's how I'd do that. So now we'll go on to the additional features. So the additional features that I added was I added paper clips for a food transportation system. So I just super glued them on the back. It was really cheap, which was good. The only bad thing is it can only carry light objects unless I increase the motor speed. So for example, it carries my crisps. Then I did build the hardware for the ultrasonic sound sensors, which is good because it stops the robot crashing into walls, unlike the tactile sensors. So it senses the environment, which is good. However, I didn't manage to complete the program for that, and then I added some googly eyes as a bit of fun. Some ideas for the future. So getting the robot back online, rather than it just going around in a circle, I'd use the previous data so it knows which way is the most likely way to get it back online due to the previous data. For my ultrasonic sound sensors, I'd like to do the programming, because at this stage I only got it to drive and stop when it gets close to a wall and then spin round, not do the full challenge for it, and then create a menu for the users, so that rather than flash the program to the robot every time, they could just input a value to do what weekly challenge they'd like. So yeah, thank you.